Hi, good afternoon, everybody, and good evening, good morning, wherever you're joining us from. And welcome to our webinar series called Experts Speak in association with IAPAC, the International Association for Business Analytics Certification. Today, we have with us the founder of IAPAC, Mr. Hans Wokers, joining us from the Netherlands. And he'll be doing the introduction for our speaker for today, Mr. Himanshu Vaidya. Over to you, Hans.
Thank you. Hello, everyone, at this webinar. I want to introduce you to our keynote speaker of today, Himanshu Vaidya. Himanshu is driving the quantum computing industry in India by working as a thought leader and also as an influencer with many academic institutions here. He has designed and developed multiple software products and platforms on big data, artificial intelligence, mesh computing, edge machine learning, and code analytics. He has established centers of excellence in big data and AI in the Europe, Middle East, and Africa regions, and has worked in India as India head by establishing more than 120 teams. He has worked on a wide spectrum of scientific and commercial data, like satellite data, telescope data, astrophysical data, ERP data, and data from scientific instruments in geophysics, chemistry, and material science. So this is somebody with a very broad spectrum and a very broad experience in theory as well as in practice. And I hope we can learn a lot from him. I have the honor to introduce to you Himanshu Vaidya.
Thanks
Please,
a lot.
Himanshu, here's the floor. Yeah.
Thanks a lot, Hans. Ram, can you please allow me to start the video and share the screen?
Just a moment, Himanshu. Can you start sharing your screen now?
Yes, I'm able to. Thanks a lot. So thanks a lot, Ram and Hans and IABAC for providing me this opportunity to share my understanding on some of the emerging and next generation technologies that are disrupting the various industries that we see today and have a large impact on businesses. So thanks a lot. Shall I start, Ram?
All yours, Himanshu.
Thank you. So do let me know once everyone is able to see the screen. You can affirm it, Ram.
Yeah, it's clear.
Perfect. Awesome. So thank you everyone for joining today. The topic of today's talk is AI fundamentals needed to stay relevant in the generative AI and quantum AI age. As we all know that these are the two most disruptive technologies that we foresee today that are disrupting various different industries. And I will share my understanding on these different technologies from a perspective where an industry professional as well as an academician who wants to learn these technologies, what are the core fundamentals related to scientific and mathematical disciplines that one needs to learn and how they tie up to this overall evolving technology landscape. We have different types of such sessions as part of our Quantum and AI Limelight program as part of Expanse NextGen Technologies. I come from Expanse NextGen Technologies and I'm the founder and CEO of this organization, which is a private limited organization specializing in quantum and artificial intelligence related software platforms, solutions, and services. I have been working in the quantum computing and quantum machine learning, quantum AI regime from past 7+ years now. And just a second, I think the screen sharing has gone in. Yeah.
Yes.
Yeah. Yeah. So, yeah. So I'm unable to share the screen.
Just a moment, Himanshu.
Sure. Yeah, I'm able to. Thanks, Ram. Yeah.
Yes, suspect.
With working from past 7 years on quantum computing and quantum artificial intelligence, as well as in the artificial intelligence and software development space from past 21, 22 years now, more than 2 decades, I would be more than happy to share the insights on some of the technicalities related to what fundamental scientific disciplines one need to study in order to stay relevant in this rapidly evolving technology landscape. So when we talk about artificial intelligence, may it be the latest discipline of artificial intelligence called as generative AI, or may it be quantum machine learning or quantum artificial intelligence, in both the cases, it is very important for us to understand the from where this all starts. And from that perspective, I would say that it is very important for us to understand the life cycle of data and then insights generation out of this data. So especially everything starts from data. When we talk about data, data is something which is generated by various different instruments. With the advent of computational machines, okay, which were invented to process this data. In initial days, there were different systems which were mechanical, and then that evolved to electrical, electronics, and then with very large scale integration. And with the internet revolution, that is the dot-com bubble after 2000 AD, there was a very rapid evolutionary, I would say, exponential increase in the volume, variety, veracity, as well as the 4 and 5 V's of big data, as we call today, velocity as well. So the speed at which today human beings are acquiring different types of data, the amount of that data, the uncertainty with which we are getting different types of data, that is called as veracity, and the variations in the nature of the data, that is whether it is image, video, or text data, numeric data, etc., are all combined together in social media profiles, for example. So from that perspective, when this flood of data started coming up after the dot-com bubble, we call it as big data. And then this is a typical big data life cycle in this slide, which talks about just a second, which talks about how one starts the overall big data data pipelines, and then from collection of the data to analysis of that data. And before that, we do, so in the first place, we do data collection, then actions on that data. Then there are some decisions that we do after processing of this data, and then we visualize this data for executive management stakeholders or the general public, depending on what type of business it is, whether it is B2B or B2C, and what kind of application or solution we are providing in terms of the deployment of the software system. Let's move to the next slide. In this slide, I have briefly explained the evolution of data analytics paradigms. So especially in initial days, it started up with descriptive statistics, as we call it today, where, let's say, people got Excel sheets to work on, and then people tried analysis on different types of variables that we put in different columns in Excel sheets for numerical data, then alphanumeric data, and different types of graphs could be generated through this, which would be essentially application of statistics to the analysis of data and then generating insights out of them. The next level to this started essentially when we started getting huge amount of data. That's first thing. And then huge amount of computational speeds with the advent of machines that were capable of processing huge amount of data, which was not possible, say, 70 years before, because we were not having very high-end computing machines at that time. So both the computational speed, the storage capacity, as well as the overall implementation of schemes related to data processing and insight generation started evolving based on the famous Moore's law, as we all know today. which states that that with the advent of very large scale integration technology, where more and more circuitry could be embedded on a smaller and smaller size silicon chip wafer. Based on that, we got the evolution of big data technologies rapidly coming into the landscape. And then with that advent of that, a particular technology called as machine learning started evolving, and which had applications in diagnostics analytics and predictive analytics. When we talk about diagnostics analytics, it is like if you have data about a particular system, which may be a laboratory, or maybe a plant, which is maybe a power generation plant, or maybe engines of aerospace, related to aerospace or submarines, etc. So, or maybe even the air conditioning in my room. So all different heavy duty equipments, if you mount sensor on them, then with the real-time data that would be collected with the integration of IoT devices on top of these machinery, we could generate the data, and then based on mathematics and statistics applications on this data to generate insights and the underlying physics and mechanical engineering of the device, we could do a lot of diagnosis. In a similar fashion, when a doctor diagnoses a patient based on different types of parameters, um, uh, in big data systems or real-time analytics systems, diagnostics was possible. And the next level to that, called as prognostics, which talks about the prediction of what will happen next. So diagnostics analytics and predictive analytics are natural progressive stages in the evolution of analytics in general. And then when rule-based, which is based on the business rules, if we combine the machine learning-based insights along with the rule-based, business rule-based know-how that we had, prescriptive analytics started becoming possible. With real-time data related to image, video, natural language processing, something called as cognitive analytics started coming into picture, which we will definitely discuss in subsequent slides. Then techniques for artificial intelligence. Again, this diagram, similar to the big data one that I showed, both of these diagrams are taken from as a reference from the International Standards Organization. This is especially from the IEC JTC1 SC42 standard, and where so many people across the globe sit together and define a particular discipline. So we can, the most important thing about this slide is that we can definitely see how artificial intelligence is having contribution from multiple disciplines. And these disciplines, in some cases, are related to the know-how that we have developed about natural languages. Some are advanced disciplines of mathematics, like statistical processing, cognitive sciences. So there are some sciences which are not into the natural sciences disciplines. They also contribute to the evolution of artificial intelligence. And then overall big data processing, structured data, unstructured data. This is to just give a glimpse of how we can segregate different disciplines and understand which particular discipline is contributing and what would be its role. So this is especially a slide that indicates about a thought process that we should develop amongst ourselves to dig deeper into a particular advanced discipline, like say, like big data analytics or advanced analytics, what we call today, or deep neural networks, and then move towards the fundamental science like mathematics, statistics, physics, and what sub-disciplines of these sciences are contributing in making the respective advanced technology or the technology discipline a reality. Now, this is about artificial intelligence. Earlier, I talked about analytics. Prior to that, big data. And big data, analytics, artificial intelligence, and next is quantum tech. So when we talk about quantum technologies, there are some more disciplines that play a vital role, especially physics, mathematics, human sciences, engineering, and computer science. Now, quantum technologies especially is a completely new paradigm in the way we do computation today. From this perspective, it is very important for us to understand the background of quantum technologies, but because the talk is more focused on AI fundamentals, I will cover up the AI fundamentals first and then move towards the quantum tech. I will try to cover up all different slides that I have within 45 to 50 minutes, and then last 10-15 minutes would be open for question and answers. So going ahead, what is important here is that there are certain disciplines I would like to call out here, like information theory. Okay, so the discipline, the sub-discipline of information theory, which falls under computer science. Again, computer science is an advanced discipline of mathematics where we have theoretical computer science, and automata theory evolved earlier based on Turing machines and different models of computation. Then the way we define algorithms and design and analysis of algorithms play a vital role here. And along with that, there are several other sciences like human sciences which play a vital role in defining the computation as well as the artificial intelligence part in quantum machine learning and quantum AI. So again, linear algebra is one of those disciplines in mathematics which plays a very vital role in both machine learning, artificial intelligence, as well as quantum technologies. Along with that, Fourier transform or signal processing is a very, very crucial discipline which one needs to master in order to understand the nitty-gritties in some of the advanced technologies like quantum technologies and AI technologies. So moving now again back to the basics, here I would like to share my understanding on computational paradigms, especially the computing paradigms. So whenever we started generating data, it is very important for us to understand that early generation calculators then got evolved into computing systems, which was based on von Neumann architecture, which essentially talks about that there is a central processing unit in which there is a random access memory, and then there are input and output devices. So which means that there is memory part and there is a processing part or component in the overall architecture of a modern day classical computer. Based on this, all different generations of the classical computers that we see today, including this laptop, my mobile phone, everything has been traditionally based on this particular type of architecture. But if we go back into the history, we will see that there are various different paradigms in which we can actually store, process, and transmit data. So when we talk about storage, processing, that is computation on that data, and then transmission of that data, all different things come into picture. So data at rest and data in motion or data in transit. So based on whether our data processing is related to a continuous variable or discrete variable, we define it as analog or digital computing. Then again, different types of systems that we use to do the calculation and storage information processing. Based on that, we can further classify them as mechanical computers, electronic computers, and then before that, there were electrical computers as well, so vacuum tube diodes and other fundamental components in electrical circuits that were used earlier. Then when we got electronics, semiconductor electronics coming into picture, we could do the logical processing of data from a gates perspective on smaller and smaller area on a chip. So that is where the chip technology came into picture, and that's where the evolution of all 5 generations of current day classical computers actually talk about. The next generation computing is quantum computing, especially, which talks about so the next generation computing is quantum computing, where Richard Feynman, one of the famous physicists in the world, actually talked about how we can use quantum mechanical systems, which means that the nature of the subatomic scale universe, which describes different types of phenomena today, that the theory in physics is called as quantum physics or quantum mechanics. And based on that, if we can use these systems to do calculations and computing, This was the idea posed by Richard Feynman when he was the first one to provide a simulation of a computing machine using quantum mechanical systems called quantum simulator. And then people started working on this analogy, and quantum algorithms came into picture. So typically 30 years back, people started working on theoretically on different types of algorithm. One of the Nobel Prize that Peter Shor received was based on his famous algorithm called as Shor's algorithm, which is essentially an integer factorization algorithm. Period finding is one of the crucial component of it, etc. But essentially, there are various different ways in which subatomic scale systems can be used to store and process information. And the fundamental unit in quantum computers to represent information is called as qubit as opposed to bit. And these are different types of ways. For example, adiabatic or quantum annealing based quantum computer, superconducting qubit based quantum computer, which Google, IBM, most of the people have this type of computer. Trapped ion, IonQ is a company. Then neutral atom, photonic quantum hardware, Xanadu is another OEM which is manufacturing these types of devices, etc. And the list goes on. And then apart from these, there are some other nature-inspired or biological analogs of computers, which are like DNA processing in human brain, community intelligence, etc. And there are like chemical computing, biological computing. There are different types of paradigms. So one needs to understand some of these paradigms in order to understand the current generation quantum computers. So we have certain classical representations of quantum computers, which are essentially classical high performance of computers or supercomputers that are simulating a quantum computer. And there are two variants in this, which is called as quantum inspired and quantum emulators. And then the difference between them is based on the way you actually develop these algorithms. For example, classical algorithms running on classical computer inspired by quantum algorithms is quantum inspired, while quantum emulators are the ones which are running quantum computers coded on classical computers for training, debugging, and testing purposes. So from a perspective of testing of the end-to-end quantum pipeline, we can use emulations using classical computing technologies. Apart from that, these are the ones which are real quantum computers, which is analog quantum computers, in which we have again quantum annealing computers and analog quantum simulators. And apart from that, we have digital quantum computers, which are essentially gate-based quantum computers. There are again two variants in that. One is the noisy intermediate scale quantum computers and fault-tolerant quantum computers as well. And these are the original equipment manufacturers across the globe, the companies who manufacture these types of quantum computing hardware. Unconventional computing paradigms, as opposed to this, includes natural computing, in which we have computers using hardware from nature, that is the natural processes in computation, and then nature inspired. So some of the ideas that come through nature, for example, evolutionary algorithms, neural networks. The idea essentially came from studying the neural networks in our human brain. And then essentially we started developing a mathematical model of the same. And then as and when we got big data processing capabilities, deep neural networks are very popular today. Generative AI is a technology completely based on this particular paradigm. Apart from that, we have different types of computing paradigms which are mentioned in this slide. Then high performance computing, or essentially supercomputing, is a paradigm where we essentially do big data processing. So you need high data storage capacity as well as input output throughput, then high precision floating point computing, and then essentially because, for example, NVIDIA is manufacturing GPU-based high performance computing clusters, which are exposed through clouds to various different users across the world. And that is where HPC becomes a very important technology, because this is the basis of all the generative AI models that are getting developed today. So big data machine learning is something which is possible because of high performance computing clusters available through cloud, and they have a scale out infrastructure, which means that we have huge amount of infrastructure available from both storage as well as compute perspective, so that very highly complex neural network models can be trained and then also tested, validated, and deployed for their use. Quantum computing, on the other hand, is more relative to smaller data size but larger state space. So there are very specific problems which can never be solved using classical supercomputers, which can be solved using stable quantum computers. And we see that original equipment manufacturers are still trying to work out and take us from NISQ era to FTQC, which is fault-tolerant quantum computing, and then beyond, which means that if we have fault-tolerant quantum computers, then many different algorithms then actually can be used. And again, scale is also one thing in quantum computing, but we are looking towards various different players in this particular area who are developing different quantum computers using different types of technologies, and a combination of these technologies along with AI, that is big data and AI, is definitely going to make a revolution. So my personal PhD that I'm doing in quantum artificial intelligence is especially related to quantum artificial intelligence and hybrid quantum classical AI algorithms. So I have been working on the intersection of quantum algorithms and classical machine learning and deep learning models, and how they can be combined together for solving real life problems related to various different industries or businesses. So complex deep learning models can then further be optimized using some of the quantum computing implementations. Similarly, some simulation for subatomic scale systems like drug discovery, etc., is possible through trapped ion-based quantum computers. And these are some of the application areas that I will cover next. So when we talk about quantum computing, where does it all started? So basically, there are supposed to be two main revolutions in quantum computing. The first revolution talks about the manipulation of group of quantum particles, that is photons, electrons, and atom interactions. So as I speak, it is very natural that for understanding quantum computing, quantum simulation, quantum telecommunications, quantum artificial intelligence, it becomes obvious that one needs to have some background of the fundamental physics which gets applied to develop the quantum computing hardware. But from software development perspective, there is computer science fundamentals that become more relevant in especially development of quantum simulation programs, quantum computing algorithms, and quantum machine learning algorithms as well. So these technologies started getting developed just after the Second World War, and we see all these applications getting mainstream into large-scale production and manufacturing. This was called as first quantum revolution. Second quantum revolution especially started post 1982, which is focused on manipulation of superposition and entanglement of individual quantum particles, and this gave rise to quantum computing, quantum telecommunications, quantum cryptography, and quantum sensing as well. So these are the typical quantum communications technologies that are relevant today, and this is pretty much mainstream. Quantum random number generations, quantum key distribution protocol, and development of quantum internet. By the way, everyone is using 5G, but Japan has recently launched 6G in their country, and 6G, there is a famous IEEE paper which talks about different types of components that a 6G internet would encompass, and that has quantum machine learning as one of the crucial component in defining as well as rolling out quantum 6G networks into production. And again, there are certain classical technologies like quantum resistant cryptography, which is also called as there are two variants again, the post-quantum cryptography and symmetric keys-based cryptography. We will not go into the details of this, but this is just to give a glimpse of what these technologies are and how they boil down to some of the fundamentals related to communication. So when we talk about classical communication through wired or wireless networks, again, networking fundamentals and protocols and algorithms related to the communications, classical way of communication become important, because based on that only we understand the fundamentals of communication technology, and then we use quantum computing paradigms in order to implement specific applications related to communications, which are called as quantum communications technologies. Again, quantum sensing technologies is a very recent and nascent field which several countries are working on today, but we see certain applications across different areas, especially medical as well as aerospace, aviation, etc. Yeah. So clocks, spectrographs, radars and lidars, ultra-sensitive imaging equipments, gyroscopes, sonars, gravimeters. So especially these sensors are ultra-sensitive to detection of certain fundamental physical quantities like gravitational field or magnetic field, and that's what make quantum sensors very prominent in certain applications related to oil and gas, mining, etc. So again, based on the current today's topic, this slide specifically talks about how quantum technologies encompass various different disciplines. For example, physics is at the core. Then mathematics, we need linear algebra, quantum algorithms. Again, Fourier transform is a very crucial part in quantum algorithms. Then engineering, we need different types of applications of engineering. Then physics and engineering combined, and then they can have a geopolitics and social impact by application of these technologies. This is a slide which talks about some of the fundamentals related to understand quantum computing. For example, understanding what is a qubit, the basics of qubit, then different use case assessments, the algorithms related to quantum technologies, error correction codes, measurement-based quantum computing, and how to do error correction on measurement-based quantum computing, then enabling technologies for quantum, atomic energy transitions, linear algebra, photonics, and non-Gaussian states. So these are some of the concepts that are put here, and the most important one is complexity theory and post-quantum cryptography for quantum communication algorithms and or applications, and complexity theory for understanding quantum algorithms and quantum software development specifically. Because complexity theory is very closely related to models of computation, there are specific models of computation which are applicable for quantum. And I will not go into the depth, but these are some of the disciplines which are very, very fundamental to algorithm development. And one can go to MIT OpenCourseware and also learn about what are these different types of models of computation and which are applicable for quantum specifically. And this is again one more level deep dive on the complexity classes, and out of which are the quantum complexity classes. So we have the computer science professionals know about hash P complete, NP hard, P versus NP, etc. NP complete complexity classes, computational complexity classes. And then we have quantum Berlin-Arthur, bounded error, quantum polynomial time, etc. So this is something which is the fundamental basis of some of the disciplines which are essential to understand the impact and development of quantum algorithms and associated software applications. So I will skip this because we will take the questions at the end. Now I will dive deeper into artificial intelligence and what it means. So this is a topic which most of the people are familiar about. But this particular definition talks about the MIT definition, this famous MIT OpenCourseware lecture, which talks about basically algorithms enabled by constraints exposed by mathematical representations that support mathematical models targeted at both thinking, perception, and action. So if reinforcement learning, perception, how to process the data, and then implementation of thinking like neural network, and all these three things combined to implement an AI system is something which is an MIT definition. You can go and understand what is machine intelligence based on Wikipedia definitions. But this is just to give a primer on how I particularly start learning a discipline. I go to Wikipedia, I go to some of the open courseware, understand the fundamentals of the subject, and try to relate it with the fundamental sciences like mathematics, statistics, physics, chemistry, and then try to weave it all together, because that actually the joining these loopholes actually gives us a holistic perspective about any advanced discipline. Then definitions of machine learning and deep learning. Machine learning is essentially talks about the mathematical models that we develop called as machine learning models that actually learn from the input data that is provided to them. And machine learning and deep learning are specifically based typically on neural network, deep neural network. Again, deep neural networks are not the only ones which implement deep learning, but still most of the most popular way of implementing deep learning approaches is using deep neural networks, which are essentially quite deep neural network layers. And what it is, we will quickly cover in the next slides. And then there are different types of inferences that we can draw from images. These are all physics-based laws and represented in a pictorial form. So this is something a human can immediately understand, which is so I have given this slide to understand narrow AI basics, basically, where for those who have physics background can understand and infer from these diagrams. But somebody who is having a psychology background may not be able to understand. So which means that humans have developed a capability based on their cognitive inferential ability. And that is very, very important to shape up the AI systems that we know today. So that's where AI becomes a multidisciplinary and interdisciplinary field where cognitive sciences have a huge role to play. And there are certain aspects in which artificial intelligence is better as compared to humans, but there are several very basic tasks related to common sense in which humans can do it very smoothly, but AI systems, it takes a lot of training to make AI systems equally capable to the brain of a small human child. Then, based on the AI technology landscape, various different applications of artificial intelligence exist today. And again, there are different fancy technologies and names given to technologies, but ultimately everything boils down to how one connects it to what we learn in our school, colleges, and graduate studies. So this is very, very crucial, because ultimately, if we are able to understand, oh, neural networks, so that actually talks about a mathematical model where neurons are there and how you implement that, what is activation function, etc. And accordingly, if we are able to tie up these gaps in our understanding, it will be much easier, and all these fancy next generation technology terms become easier to understand. These are different types of AI software, so I will not go into the depth of this. So we have like AI software platforms, conversational intelligence software, machine learning software, deep learning software, etc. These are just examples given. Then different schemes related to machine learning models exist, out of which the most famous ones are supervised versus unsupervised learning. So if you tell the machine learning program that this is a labeled data, these are apples and oranges, and then you give, let's say, thousands of apples and oranges and train and label them, and then eventually after training the model, you give a completely different set of apples and oranges, and it is able to classify. That particular type of learning is called as supervised. If you do not tell anything without labeling, so unlabeled data set is unsupervised, and there is something in between called as semi-supervised. There is something called as self-supervised, which is more into the deep neural network context, which we will also deep dive later. So artificial neural networks, again, from a technology perspective or from a scientific theory point of view, these are basically, the term is connectionist systems. So which is very, very important. And how they evolved, I will not go in depth because this is plain Wikipedia definitions. Then artificial neural networks started becoming very popular, especially for big data machine learning problems. There is something called as hyperparameter tuning, architecture of different types of neural networks, and algorithms which help us to train a neural network like backpropagation algorithm, etc. These are some of the details related to learn artificial neural networks, which are essential to implement deep neural network algorithms. Deep neural network models. Then neural network types of neural networks, there are cheat sheets available, and these are type of the architectures of neural networks, which we will not go in this particular session in depth. Then as opposed to machine learning, so deep learning is a subset of machine learning, and which has deep neural network implementations, which it is called as deep because it has multiple hidden layers in it, and there is input and output layers. And then the types of these layers, these are nodes basically which store some type of data, and then there are operations on that data. Typically it is additions and multiplications, and there are different weights given to these edges to this neural network graph, and then you convert the linearity by applying a particular nonlinear function called as activation function. But this is essentially just in mathematical terms, what neural network does is basically function approximation from mathematics point of view. And then this technology started evolving based on the advent of big data, because now all the patterns that were hidden in the data were available for large deep neural network systems, and then these type of systems could learn from the big data. So big data machine learning actually made neural network technologies popular, because neural networks were invented several decades back. But before the dot-com bubble, they were not that popular. They were still implemented in the academic community. Then in around 2012 or so, this is famous transformer architecture paper, which has multi-head attention as one of the components in the implementation of the architecture, and which started the generative AI revolution. And then there were several papers, again, convolutional neural networks, etc. In GPT, generative pre-trained transformer models, which is again transformer model. So transformer is a type of neural network. You will see here that different types of models exist, out of which transformer models started becoming more popular, especially for natural language processing and natural language understanding applications, and which gave rise to generative AI. So what is generative AI model? Especially, it is different from machine learning model in a sense that it can generate a completely new content. And that is where this deep fake and other technologies started becoming popular and started gaining attentions in today's world, because you don't need labeled data set for generative AI models, because they are trained on huge, immensely huge corpus, data corpus we talk today. So all the data that we are talking about is getting absorbed by the assistants like Google, etc., Amazon Alexa. Essentially, all this voice, text, image, social network data was fed to develop these GPT-based architectures and voice-to-text deep neural network implementations for Google Assistant, etc. And because they have so much amount of data, some of the generic patterns related to conversations between two human beings could be actually extracted out of that data. And that's what generative AI has, the capability of generalizing a lot of inferences related to natural language as well as image processing. So what is generative AI? Especially artificial intelligence has a subset called as machine learning. Deep learning is a subset of machine learning. Generative artificial intelligence is a subset of deep learning based on transformer neural network architecture. Large language models is a type of GenAI model, which is specifically targeted towards language-related inferencing or intelligence gathering. Generative pre-trained transformer is a specific type of neural network architecture, LLM. And then GPT-4 is based on GPT architecture, and ChatGPT again. So this is the type subset of GPT-4, etc. Again, in the OpenAI context, you can see GPT, DALI, Codex, Vision to video analyzers, different types of applications that generative AI has. How generative AI works, it starts with initial stages of generative AI data collection and processing. Finally, you get an output, whether it is text, images, or feedback loops. It goes through feedback loops and eventually provides you the content that is needed. And then there is an iterative refinement that happens in the overall way in which generative AI works. So if we break down different key features and the differences between them, machine learning versus generative AI, the key differences lies into creating a new content, especially, okay, and what type of differences in architecture, model architecture, etc. exist. This particular slide talks about that. And that's where I would end it. Before that, what I would like to do is on quantum computing, again, there are a couple of slides which I will not go through, but I will just quickly walk you through what is quantum computing, essentials. Again, in a similar fashion, the definition of quantum computing, it's based on the study of a non-classical model of computation. Then quantum information processing is one of the crucial disciplines that one needs to study. Quantum complexity theory is another discipline that one needs to study. And then these are different types of ways in which you can simulate a qubit. I will not go into the in-depth thing, how a wave function, this is typically called as a wave function and the details of quantum physics. But a detailed comparison between bit versus qubit from a mathematical point of view, physics-related point of view, and logical information processing point of view. And then when we call that a particular quantum approach is so much better that so much of $1 million investment is worth it, then it's called as quantum supremacy, quantum advantage, limited quantum speed up, the difference between them. And then different types of applications for current generation NISQ-based quantum computers, the quantum simulation, machine learning, optimization, and other algorithms. And then a couple of revisions related to quantum communication, etc. What is complexity theory, quantum complexity theory, what are quantum algorithms? They are based on the quantum circuits, and how do you define a quantum software program are some of the fundamentals. Then 4 patterns in which how you can represent the classical and quantum data in different based on the representation of data and the type of algorithm. And then the definition of quantum machine learning. So which means that for quantum machine learning, you need quantum information processing and machine learning, and the intersection of both actually has this fantastic field called as quantum machine learning or quantum AI algorithms. And some of the challenges related to quantum technologies. These are different quantum technologies that are available today. And these are the disciplines, for example, linear algebra, mathematics and statistics, quantum physics, superconducting physics, photonics, and quantum optics, algorithms research, machine learning, deep learning, AI, algorithms, Fourier transforms and digital signal processing, networking and communications, and systems engineering. In my opinion, some of the crucial disciplines that one need to study for understanding quantum technologies are these ones in the right side. And then these are different trends in quantum technology and AI also. AI is already applicable for different types of these fields. In NLP, natural language processing, natural language understanding, 6G or quantum internet, quantum cryptography or data security, finance, healthcare, advanced research, and space communications and research are some of the areas, including medical research as well as pharmaceuticals, etc., are some of the fields of application for quantum and AI tech. And that concludes the session today. I was given 45 to 50 minutes to cover it up, and now the forum is open for questions and answers. Over to you, Ram.
Thank you so much, Himanshu. Really appreciate it. So we have a few questions from our attendees here. So Abhinesh Ravi is asking, what are some strategies for collecting and preparing data for AI models?
Okay, sure. So Ravi, I will try to briefly throw some light on your question. So there are various different strategies in which you can collect data. In some cases, the data you need to do web scraping, especially to get the data. If your problem statement is related to social media, but if it is related to a very specific industry, then you will need to get the data from that industry specific customer or some open source data sets related to that industry. For example, for banks or fintech, there are some synthetic data sets available which one can use to train the models. But to get a realistic application of machine learning or deep learning AI models, one needs to extract the data, do some pre-processing on that, convert it into the right format so that then it can be fed for a machine learning model. So before one actually feeds up data, there are certain stages in the end-to-end data and AI life cycle, which I did not cover. There are machine learning operations life cycles as well, which are defined. So data ops and ML ops are some of the very important technology disciplines that are applied in the industry today in order to, and in the initial stages of this actually talk about data pre-processing. If there are missing data, then how can you throw that data? Is it relevant to throw the data? And all these decisions are taken in combination with the business specific rules. So one need to define what to do with the missing data. Should you replace it with the average value for that particular variable, or should you simply reject it? What would be the best strategy? Is it if the data is having veracity or it is uncertain or it is having missing values? So how much missing values are permitted? What percentage of them? All these decisions are something which are taken by machine learning engineers and data scientists while implementing practical applications. So I hope I answered that question. We might move to the next question.
Thanks, Himanshu. One of the anonymous attendees is asking, how can non-technical professional leverage Gen AI tools in daily work?
Okay, so with the advent of generative AI, there are two types of usage. You can see one can actually use the ready-made tools that generative AI provides. So there is something called as developing generative AI models. For example, I want to develop my own chat GPT. It's very difficult because huge millions of dollars are required to develop a single large language model or a large vision model. So, but there is something called a small language model or small vision model, which one can think of if you are developing it for a specific purpose, but to reuse the potential of existing Gen AI models, which are pretty decent in terms of inferencing from input data. So if one is a developer, there is a process, different types of processes like prompt engineering and prompt tuning. For example, ChatGPT, the right type of question is very relevant in getting the correct answer from ChatGPT. And that type of technique is called as prompt tuning or prompt engineering. So there are various courses available where people just want to use them as a user. For example, I do not need to know how Microsoft Word or Excel or PowerPoint was developed. I just need to know how to use it as a tool. From that perspective, prompt tuning, prompt engineering, understanding how to send prompts for a particular language, say English, to ChatGPT and similar tools and get the relevant information is something a non-technical person can definitely learn and apply these tools in their respective fields. The techniques are prompt tuning, prompt engineering. Then if one is a bit technical, then there are certain other things which come into picture, like retrieval augmented generation and fine tuning and then further enhancing and doing transfer learning on existing GenAI models, which is more for a technical person. But for a non-technical person, one can still use it as a tool for mainstream purposes for which they are meant. If it is a very specific purpose for a particular industry, say medical or healthcare or pharmaceuticals or fintech or retail, in that case, you need to actually use transfer learning approaches to make sure that the model can actually provide insights for the data sets related to your business domain. So,
Thank you so much, Himanshu. We have one more from one Mr. Shah. He's asking, do I need to integrate the chipset with Neuralink to prepare that for quantum computing? I'm not clear on what is.
no, so neuromorphic computing is a different discipline altogether. So the chipset, there are certain hardware types like ASIC hardware, etc., FPGAs. I did not go into the detail of that, but quantum computing is different from neuromorphic computing. What we are hearing that some company of Elon Musk has invented a chip which can go in human brain and which can collect the data. That is not quantum computing. Quantum computing is utilizing phenomena related to atoms or subatomic scale systems in order to store, process, and transmit data. And the most famous type of quantum computer today is superconducting qubits. It requires huge amount of investment. So you can Google search and you can see what type of computer Google has made or IBM. It's all based on something called a superconducting qubit technologies, a superconducting loops, where they have to go to absolute zero temperatures in order to maintain these systems because they are very much vulnerable to noise. That's the current generation state of quantum computing hardware today. But there are several other approaches like photonic quantum hardware, trapped ion-based quantum computing hardware, etc., neutral atom, then analog quantum computers, etc., which have specific applications to various different fields. So people are trying to now develop chips related to quantum circuits on which you can implement quantum circuits, and then these chips can then be scaled out in a similar fashion the way we did VLSI several decades back. But that technology is still evolving. But the way research is progressing, I foresee that if 2035 is a time when mainstream large-scale quantum computers are envisioned to be a reality, I foresee that mostly 5-7 years prior to that itself, we will have some of the great applications of mainstream quantum computing hardware for large-scale quantum computing. So,
Himanshu, I have a question from my side.
sure. Yeah.
How
Yes.
much of a game changer was that recently the thing what came out that superconduction at room temperature for LK99? The scientists who actually from South Korea managed to say that what they've been doing this study from 1999 onwards. Lee Kwon and one more of his person from South Korean team, they've been working on creating superconductors at room temperature.
Okay.
Right now, superconductivity is all at minus, negative,
Negative minus
very,
2.
very cold. When you take up attaching the cooling system to that superconductivity is what actually is making quantum computing very expensive. But bringing superconductivity at room level was a game changer. And I know that thing LK99 as a superconductor at room temperature kind of faded away as a breakthrough. But I know somebody somewhere is working on it. So what kind of a game changer would have that happened if at all that became a reality, where you could actually conduct cheap materials and create superconducting materials at room temperature?
Yeah, so I will have to go and read in detail, but what I personally know is that even if somebody developed the way to implement superconducting loops at room temperature, that definitely would be a game changer if that is true. But it also again that's not the only problem, that keeping it at low temperatures. There are certain other problems related to quantum computing, like the noise involved. the noise can still be an issue, even if the good thing is that you will not require that much cost in order to keep it very cool. But still, related to quantum computing, that's not the only problem. Related to developing quantum computing hardware and making it mainstream for large-scale production, there are certain other problems, like they are very much prone to noise. So whatever are the radio waves, different types of electromagnetic waves that we get, cosmic rays, these are ultra-sensitive computers, which again can get affected. The readings of computation can get affected and distorted because of this type of noise. Secondly, the calculation cannot last beyond a particular time frame. That's another problem. Then when you start scaling out, um, after a particular level, it cannot. And that particular quantity is called as fidelity of quantum algorithms. So it's not only one thing that people are addressing across the world. There are several researchers that is why working on various different approaches, and there are various different companies, including big giants as well as hardware startups in quantum. So somebody is implementing photonic quantum computing hardware. I personally feel that photonic quantum computing hardware is definitely applicable at room temperature. It has its own challenges again. So every technology has some positives and some negatives. Out of whatever 10, 50 technologies that we have, 10, 20, 30 different types of subdivisions of those particular implementations again. My personal opinion is that out of the 100 different variants in which people are trying to develop a quantum computer, even if 5 or 10 click and they are capable of solving most of the problems that we face today, I think that still can be a game changer. So I hope I was able to answer your question, Ram.
Yeah, honestly, because you know what, I was so excited about it. Actual,
If that is true, then I think
thing
definitely that would have been a game changer. But then, if that is the case, I
happened,
think Google, IBM, both are having
right?
hardware
It proved
based on superconductors. So they would immediately implement that technology in that case. So any other questions we have? I think several questions are there.
So how can somebody maintain data integrity with repetitive nature of AI? I think we are actually freezing your frame is freezing, Himanshu. If you can maybe cut your video, I think
Sure, I
we
will
actually
do
have some
that.
bandwidth issues right now.
Yeah.
Yeah. We have Edwin Okemba asking, how can somebody maintain data integrity with the repetitive nature of data in AI?
Repetitive nature of data and AI, I did not get the question completely.
Yeah, me neither.
So repetitive nature of data, I did not get. Do you mean to say that uh, patterns in a similar type of data, or
I think so. I think
yeah,
so.
I
That's what
think
he's trying to.
because in real-time systems, when you have sensors mounted on devices, one can get repetitive data, time series, for example, and then there are variations into that. So it depends on what type of pattern we want to infer out of them. Okay, so maybe we can move to some other questions like how close are we to quantum computational models breaking cryptography? So we already have an algorithm. For example, Srishti Adhikari has asked this question. So we already have Shor's algorithm, but for that we will need a million qubit quantum computer, which is immediately not a reality. But there is something called as RSA encryption scheme. So RSA 2048 bit quantum encryption. So basically existing encryption technologies that are used in all type of communications today. Quantum computing algorithm like Shor's algorithm pose a great threat to that particular technology. But again, people are using either quantum key distribution protocol based approaches or post quantum cryptography or a combination of both in order to make sure that we have secured data before these type of quantum computers become mainstream. And that is where a lot of business related to data security is available for quantum computing organizations like us. So,
Yeah, Himanshu, if you can see any more, one last question which you feel.
yeah.
I'll leave it to you to pick it up from the Q&A section.
Okay. So, what course on quantum computing can be taken by non-computing graduates? So, I would typically recommend to do some of the homework on understanding the fundamental disciplines first, and then move on to several courses. Like we have our own course as well. Like Expanse Next Gen Technologies has its own curriculum on 3 different types of courses: fundamentals of quantum and AI science, which is focus, followed by quantum technology bootcamp and AI technology bootcamp. And there are several others across the world. People are providing it. So you can check that on our website, as well as there are certain courses in India as well as abroad, which are available. And people are getting into quantum computing education very recently. So you can know more about me and my company on our website, which is www.expense.com, and can get more information about our company there. And if you have any questions, you can also follow us on LinkedIn and on our website. So that's it, Ram. Thanks a lot for providing this opportunity.
It's been brilliant. Actually, we have one of our participants asking, he wants a complete session dedicated on quantum computing. So we will look at it if it's in the works in the coming days. But anyway, to all the participants, I hope we have put up a Google Sheet in the section where you can enter your details to get your IBAC attendee certificate. And please visit iabsc.org to become an authorized training partner. And we will keep you all posted on our upcoming events, email or across all our social media platforms. And looking forward to connecting with you all soon. And thank you again for attending today's session, and have a nice day, everyone. Thank you, Himanshu, as well.
Thank you, Ram. Thank you, IIBSC.
Thank you as well.